Hi, this is Sam Ganzfried. I'll be presenting on opponent modeling in multiplayer imperfect information games. This is joint work with Kevin Wang and Max Chiswick. So, in many real-world settings, we have agents behaving strategically and interacting with multiple opposing agents. And the goal here is to try to design an agent that can perform well against a wide variety of strategies that the opponents may be following. So the standard approach, or a common approach, is to try to approximate or exactly compute a solution concept from game theory such as Nash equilibrium. This approach is done well, for example, in computer poker competitions, where recently computers have defeated strong human players. Now, one shortcoming of this approach is that it assumes all the players are behaving rationally, and it essentially ignores observations of the play that you could potentially adapt to and exploit if they're mistakes. So the ultimate goal in strategic multi-agent environments is to obtain a high performance against a wide range of realistic opponents that are playing unknown strategies. Now, in practice, so this is called opponent modeling, sort of in contrast to just Nash equilibrium. And so in practice, we might have some information available that we'd like to be able to take into account to exploit weaknesses of the opponents. This information could take several forms, one of which is historical data of past play. And so this data, if it's available, it might be specific to our actual opponents, or it could be from some general population which we expect our opponents are drawn from. Also, this information might include real-time observations. If we're repeatedly playing against the same opponents, we might see what their actions are. We may or may not see their private information. So there's different settings that have been studied in where the private information is revealed after the play, is always revealed, never revealed, or sometimes revealed. So the setting that we're going to be working with in this project is the following. So we're going to assume there's no historical data and partial observability of the opponent's private information, which is probably the most challenging out of the different scenarios I described, because this partial observability encompasses full and no observability. Those are special cases of it. Additionally, having no historical data is more challenging than if you have data. We're also going to assume no domain-specific expertise or features. I want to note, though, that if such information is available, if we do have historical data, if we do have features or domain expert, we can incorporate these into our approach and improve performance. But in the event that they're not available, because in many situations these are not available, our approach is general enough that it's still going to be applicable, and therefore it's domain independent and very broadly applicable. It's not completely dependent on having specific features. Now, our experiments are going to be in a 3-player imperfect information game called 3-player clean poker against a set of real opponent agents as well as several Nash equilibrium agents. The opponent agents could be playing arbitrary strategies that may be dynamic. And I do want to point out that there are some significant differences between two-player zero-sum and 3-player games, one of which is that computing a Nash equilibrium is keypad hard. Nash equilibrium itself also doesn't have the same theoretical justification. And so there's some fundamental challenges that come up in this distinction between 2-player zero-sum and 3-player. And so, like I said, our approach is going to be broadly applicable to multiplayer imperfect information games in this class. So I'm going to talk a little bit at the high level about how our approach is going to work, and then I'm going to talk in more detail about each of the subroutines here and what the different inputs mean. So at a high level, what we're going to do is the following. So we're going to simulate k different strategies for the opponents, and I'll describe on the next slide how we do that. And so we're going to essentially deal just with these k simulated strategies. And we're going to use a Bayesian approach where we're going to have a prior. Initially, we're going to have a prior that's uniform over these k. So probably 1 over k over each of these. We're going to have some burn-in period where we follow a default strategy, sigma star for ourselves, and collect observations of the play. We're going to update posterior probabilities of these k. We're only going to deal in this space of k simulated strategies. And then after the burn-in period, for the remaining periods, we're going to continue updating the posterior, but we're also going to be constructing opponent model from the posteriors and playing a best response and exploiting. And so at a very high level, this is how our approach is going to work, but I want to elaborate on each of the subroutines here. So first off, how do we create these samples? So like I said, we don't have a historical database to go by. We are going to assume that we have a prior, a mean for the strategy profile for the other players. And where does this come from? Well, it could be an approximation of Nash equilibrium. It could be, for example, running counterfactual regret minimization or fictitious play, which CFR has produced very strong strategies in practice in poker. They may converge to approximate Nash equilibrium, they may not, but regardless, they should produce a pretty reasonable starting point strategy. And so we're going to use these as the prior strategy means or something else. And we're going to assume the prior distribution is a Dirichlet distribution with the mean at that prior I just mentioned, and the variance is going to be controlled by this parameter eta. So, so essentially we're going to come up with k-sampled strategies from this Dirichlet distribution. Now, one challenge when you're in the Bayesian setting is that you really don't want to have probability 0 prior on anything, because then if it actually does occur, the algorithm crashes. And so we're first going to take things that are less than epsilon and make them up to epsilon. Epsilon is going to be an input parameter of the algorithm. Then essentially we're going to sample at each information set, at each action, we're going to essentially sample from the Dirichlet at this mean that I've mentioned. And this can be done efficiently by sampling from the gamma distribution and normalizing. And so this procedure is going to compute k different strategy profiles that are somewhat close to this prior mean that we have. So next, we need to talk about how we're going to update the posterior probabilities for these k sampled strategies after each hand or each iteration of play. We're essentially, and recall, some private information might get observed, some might not. And so for each hand, I'm going to call it a hand, for each round, we're going to look at each of these sampled strategies, there's k of them, and we're going to say, what's the probability that the opponents, all of them, would have followed the observed actions and information that we saw this round if they were playing that strategy. And so we're going to multiply that by a prior that we had from the preceding round and normalize, and then we're going to get the new updated posterior probabilities for each of these k sampled strategy profiles. Now, in order to compute the opponent models from these posteriors, we're essentially going to just assume that each of the k sampled strategy profiles is played in proportion to the posterior probability that we've calculated. So for example, if there's only if k is 2 and it's 40% on strategy 1 and 60% on strategy 2, at each given information set, we're going to say, okay, we think that they're playing the action from strategy 1 with probably 0.4 and the action from strategy 2 with probably 0.6. So pretty straightforward how we do that step. And so there's a little more to it, but this is really essentially how our approach is going to be working. And so the experiments are going to be on 3-player Coon Poker, which is an imperfect information game. It was used previously in the annual computer competition. There's one round of betting, and each player antes one chip and is dealt a card from a 4-card deck. So there's an ace, a king, a queen, and a jack. Each player gets one card, and then the 4th card is put off to the side. The first player has the option to bet one chip. So each player antes one, so there's 3 in the middle. And then the player can bet 1 or can check, which means to pass to the next player. Players are not allowed to raise, and so if there's a bet, they can either call or fold. And so if someone bets and then the other players fold, then the player who made the bet wins the whole pot. if one player bets, another person calls, then there's a showdown, and the player with the highest card is going to win the whole pot. So just as an example, suppose the first player is a queen, then king, then an ace, and suppose it goes check, check, and then the ace bets, and then the queen folds, and then the king calls, then player 3 is going to win. The whole pot is going to have 5, the 3 from the antes plus the 1 that player 3 bet plus the 1 that player 2 called. And so there's going to be a profit of 3 for player 3, and player 1 is going to lose their ante of 1, player 2 is going to lose 2, just as an example. So we experimented with a set of, with our opponent modeling agent, and 10 agents that were created by students for a class project where they were incentivized, to do as well as possible, as well as 3 exact Nash equilibrium strategies. And the class agents they were free to use whatever approach they wanted. One of them claimed to use neural networks, another counterfactual regret minimization, another opponent modeling, another rule-based approaches. So they were free to use whatever they wanted, and I don't know for sure what they did use. So anyway, now let me talk a little bit about these Nash equilibria. So this game has infinitely many Nash equilibria. There's a paper that computes an infinite parametrized family, and one subfamily has been singled out as being more robust than the others. And so, and in particular, the 3 that we're going to use are going to be the lower bound, midpoint, and upper bound from this robust subfamily. So now we basically have a pool of 14 agents. For each grouping of 3, we're going to run 10 matches of 3,000 hands each, and we're going to do all 6 permutations of the agents, which is an approach that has been done before that reduces variance significantly. And anyway, so these are how the experiments were run. And so I'll talk more about the effect of the parameter selection, but for now, let me just say that we used epsilon at 0.05. Remember, this is sort of the threshold to prevent probability 0 in the prior. We used k, the number of samples equals 10. We used h, the burn-in period equals 10. We used eta, which determines the variance of the Dirichlet prior, equals 4. Now, for our default strategy, we used a strategy at the lower bound of that robust equilibrium space, because we had done some experiments previously where this had done well. We could have used another equilibrium, but basically, in general, you would want to use some sort of approximate equilibrium or some known pretty reasonably strong strategy. For the opponent's prior, we chose the strategy at the midpoint of the robust equilibrium space, because it had more entropy, it had fewer probability 0 actions, which we know are problematic for evasion prior. And so those were the sort of default prior strategies that we used. So here are the results from our main experiments. MBBR denotes our agent. The N1 and 2 and 3 are the 3 Nash agents, and then the C1 through 10 are the class agents. And so the unit here is chips per hand times 1,000. The standard errors in these units were all between 0.4 and 0.6, so all these results were significant. And we can see our agent clearly outperformed all of the others. The Nash ones also did pretty well. They got 2nd, 3rd, and 6th. But more importantly, we outperformed the Nash agents in addition to outperforming the class agents. And so now I wanted to look and say, well, what was the effect? We used this prior that the opponents were playing near this Nash equilibrium. What if we used a totally uninformed prior? So we picked, the strategy that does uniform random, that just plays every action with equal probability, and then we did a Dirichlet distribution with that as the mean. So basically uniform random and pick sample to case strategies around there. And actually, this leads to extremely poor performance. We came in 2nd to last place if we did that. So it shows that it is quite important to have a reasonably informed prior distribution. So now I'm going to talk about the sensitivity of results to the different parameters. And so first this epsilon, remember, we want to ensure that all probabilities are in the prior are at least epsilon, so we don't get, these probability zero actions happening. And so we can see actually this has a pretty significant effect. We did 0.05, we could have set it to be 0.02 or 0.01 or something, it would be, 0.02 would be fine, but setting it to be, very, very close to zero can be problematic. Setting it too high is also problematic. If it's over 0.1, performance degrades. So something pretty small is best here, 0.05, 0.02. H is this burn-in period. So sort of interestingly, I would have expected that we need sort of more in the exploration phase, but here it essentially, we used H equals 200, but it's ended up pretty similar between 0 and 200. It essentially degrades linearly because the more that we're not exploiting is profit we're missing out on. I would expect in larger games it's likely that we do need to have a bigger burn-in period and do more exploration, but this should be tuned accordingly for different games. So eta, remember, controls the variance of the Dirichlet prior. It turns out it didn't make too much of a difference. We used 8 equals 4. Looks like 8 equals 2 is slightly better. Now here, this axis on the y axis scales from 44.5 to 48.5. So these are all pretty similar. Anything 8 equals 2 to 4 seem to be best. So this didn't make too big of a difference. Now k, the number of samples, makes a very big difference, which shouldn't be too surprising because more samples means A, we're more likely to have one of the sampled strategies close to the strategies that the opponents are actually playing, and B, as k gets larger, then we're going to have our posterior is going to more closely approximate the actual, full posterior of what they're playing. But anyway, we used k equals 10. We can see had we used 20 or 30 or 40, performance gets way better. But it does increase the runtime by a factor of k to the n minus 1. And it also increases the memory. And so essentially, I think it's important. The takeaway here is that you probably want to use as many samples as possible given whatever resources you have available during gameplay. So to wrap up here, we presented an approach for opponent modeling multiplayer imperfect information games. We studied arguably the most challenging setting where we had no historical data and we had partial observability, which encompasses both special cases of full and no observability. We assume that there's no features or domain-specific information available, and so our approach is domain-independent. We expect it to be broadly applicable to multiplayer imperfect information games. It should be scalable to large games. It uses importance sampling and is sort of working in this smaller space of just k-sampled strategies, which might be significantly smaller than the full strategy space of the game. We experimented against 10 real agents and 3 Nash equilibria, and our agent decisively beat all of them. In the real world, we often encounter unknown opponents with a wide range of strategies, and it's important to be able to perform well against the goods, like Nash equilibrium or other good strategies, while also exploiting mistakes that weaker opponents are making. And so our approach was successfully able to do that. Now, one big challenge that comes up in general in opponent modeling research is the availability of opponents and benchmarks to compare against. So, fortunately we have these agents from the class project for 3-player Coon Poker, but I'm not aware even of any other games, multiplayer imperfect information games in particular, that have opponent agents readily available. So perhaps there could be a new competition that spurs research in this area. For years there was this annual computer poker competition, although that hasn't been run in several years. Now I've seen some papers where they simulate somewhat usually naive strategies for the opponents, like they make them uniform random, maybe add a little bias to it, or Nash equilibrium in some game where they sort of perturb the utilities, which, if there's nothing better to do, that's better than nothing. But I feel like doing this doesn't really properly capture, the wide range of realistic opponents that are out there. And so, it would be great if there were more availability of opponents to these games. Related to this point is that we'd like to experiment with on larger games to explore the scalability. I also want to comment and say our approach is sort of inherently or implicitly assuming that the opponents are playing a static strategy, in that we're looking at the overall frequencies throughout the whole game. And so some of the opponents were claiming to not be static, and we still obtain very strong performance. So perhaps this can still do well regardless. But I also want to note that even for the static setting, there's still a lot of open questions that remain. Like, is this approach going to be scalable? Is it convergence in the limit as you get more observations, etc. So there's still more open questions even here, let alone in the more realistic and challenging scenario where the opponents can be dynamic, exploitative, and deceptive. Thank you.